Great. So now we are recording it. Okay, nice. Okay. So today I'm going to talk about consensus formality theorem, but probably just formulate this theorem because even this will take us quite some time. We need to discuss some new ideas, which probably is not familiar to everybody, which probably are not familiar. They're worth discussing. They're not very hard, but then they're definitely worth knowing. So we are about to solve the following problem. So we have a manifold M with a bivector field pi on it. So when I say bivector field, I mean a section of the exterior square of tangent bundle of this manifold. Locally, pi is equal to pi ij to upper indices. And if you want, so the pi ij is equal to minus pi ji, so it's Q symmetric. And also, if you want to have some basis, then you can write pi as a sum over pi ij over I and j of pi ij di tensor dj. Because you know, every vector field is a differential operator, linear differential operator of first order on the manifold. So when we choose two, when we speak about bivector, it should be some kind of quadratic in vector fields, and vector fields have bases di and dj. So this notation is more or less clear from what I have just said. So anyway, you have this bivector, and then the condition we want is that the following formula actually gives you a Poisson bracket. So Poisson bracket is bilinear over scalars. That's clear. It should verify Leibniz rule. Of course, it is skew symmetric. That's clear. But the most important condition is that it verifies the Jacobi identity. I hope everybody knows what is Jacobi identity. The most non-trivial thing is somewhat a non-trivial thing here is to prove that this Jacobi identity is equivalent to the following quadratic equation. We take pi and take its Houghton bracket with itself. It should be equal to 0. It should vanish. So probably you don't know what is Houghton bracket, but Houghton bracket is a very important construction, universal construction, which exists on all manifolds. So it's Houghton bracket, in case you don't know what they are. It is some very natural construction. Suppose you have two vector fields, x and y. I believe you know what is their commutator. So locally, every bivector field pi is written in the form xi wedge xj, sorry, xi wedge yi, sorry, sum over I. So you have another expression of the same sort, say pi tilde equal to xj wedge yj tilde. Then the Houghton bracket is the most natural thing you can do with these expressions. Namely, you can say that this bracket is bilinear on the sum. So it's this bracket will be equal to the sum over I and j. Then you want it to verify the Leibniz rule with respect to the wedge product. So what you have will be some with some certain signs of x I wedge xj tilde wedge yi comma yj tilde plus or minus now xi wedge xj tilde comma y sorry, I think it's better to write first yi and then xj tilde and so on. So you take all possible pairs of vector fields which enter the expressions for pi and pi tilde and take these commutators of vector fields with proper signs. So what you obtain will be unique is a unique bilinear operation on polyvector fields. So I denote polyvector fields lambda as sections of lambda q of T M for all q from 0 to n, the dimension of the manifold, just by poly. Sorry, I think it should be T poly. T poly, because they're tangent, they're fields, and fields they're sections of tangent bundles. So T comes for this reason, appears for this reason of M. So what you get, a natural bracket, unique bilinear operation on this space, which verifies few natural conditions, like the bracket on fields is just a commutator. So when they are one field, unique field. Second, it is this graded Leibniz rule. And the third is the graded Jacobi identity. Well, unlike the usual Jacobi identity, the graded Jacobi identity comes with certain signs which appear naturally from this definition, but they're quite hard to remember. So if you want, I can find the reference for you, but not for a while, not now. We're just speaking about this a bit loosely. But what is important about these signs, it is that when you take commutator of pi and pi tilde, and you change the order of pi and pi tilde inside the commutator, inside this Houghton bracket, what you obtain will not be minus the commutator of pi and pi tilde, it will be plus the same commutator. And therefore, the condition which I wrote here, that the commutator of pi with itself is zero, is non-trivial, totally non-trivial. So, okay, we have Poisson structure on a manifold that is fixed by vector field with which squares to 0 with respect to this Houghton bracket. And then we have these Poisson brackets. Then we want to obtain the star product, which I explained is the associative product on the space of formal power series with formal variable h or h bar with coefficients in smooth functions on manifold M. And this star product should look like this. First of all, it should be linear over h bar, and therefore it is enough to write this star product only for f and g from the space of smooth functions. Then, since we said that this star product should be a deformation of the usual product, the first term in this star product should look like the usual product of f and g. But then the second term should look like this. But after this, we have a whole series of additional terms which account for the associativity of our product, and they all are written in the same form. The sum is taken over k from 2 to infinity, and here we have h bar to the power k times bk of f and g. So in general deformation theory, bk should be just a bilinear function, bilinear form from functions, smooth functions of the manifold, into itself. However, it is natural to make more assumptions on bk. These assumptions are as follows. If you're just asked what bilinear functions there can be, you can define on infinite dimensional space of smooth functions on a manifold, you end up with something totally untractable. You have no control whatever over these bilinear functions. They can be really wild. So to have something a little bit more tame, people usually assume that bk are given by expressions of the following form. They should be equal to the sum over some multi-indices of certain coefficients, functorial coefficients. Let me call it A, or probably B with indices I and J, and they should depend on points on the manifold. So they should be just functions, smooth functions. But then we should take some partial derivation corresponding to the index I and apply it to f, and multiply it by partial derivation of with index j applied to g. So if I say is multi-index I1, In, where Ik is just a number from 1 to n, then di is just the product of dik from 1 to n capital. It is just some partial derivation in direction of certain coordinate on the manifold. Of course, this is only local. This expression is only local, but on the other hand, and you change the coordinates, then from this kind of expression, you will obtain the same kind of expression, which will also be written in terms of differential operators of I and differential operators of J with local coefficients, with smooth coefficients. This expression is usually called bidifferential operators. So let us now look attentively at the associativity condition. So we want the following to hold for all F, G, and H in the space of formal power series with coefficients in M in formal variable H bar. Again, since we assume that both sides are H linear, H bar linear, we can actually erase H bar from here and only consider this equation for F, G, and H in smooth functions, Now we can write down this expression attentively. So the first term is pretty simple. I don't write parentheses here, but if I had to, I would put it like this. Put them like this. But there is no need in parentheses in this expression because the usual multiplication is definitely associative. Then the next term will look like well, let me write it like this. F GH, probably I better write it like this. FG H plus let me see. F comma G H is equal to F GH plus F GH, if I'm not mistaken. Right? So this is just Leibniz rule, I think, for for the Poisson bracket. Then the next expression will look a little more promising. It will look like this. I'll try to write it in a concise form. Probably I will mess up some signs, but don't worry about this. So it will look like this. F B2 of GH minus B2 of FG H plus B2 of F GH and minus B2 of F G H should be equal to up to sign, which I totally mess, F G H plus or minus, I think it should be minus, F G H. So if you look at the right-hand side, and if you remember that these should code for all F, G, and H, and you see that this equation is actually a condition on one hand side. But actually, the bracket verifies the Jacobi identity. I'm not going to stop at this moment here now, because I spoke about this last semester in the fall. If you want, I can speak about this again, but not today. What is more important, it is to look at this expression again and observe. And what we have on the left is nothing more but just the Horseshoe differential of the term B2. But and on the right-hand side is nothing more than this Gersten-Haber bracket of the maps given by the Poisson bracket. So I think it is proper time for me to introduce these notions, the Horseshoe differential and Gersten-Haber bracket. I think I mentioned them last year, but this time I'm not that sure actually. So what is Horseshoe differential and what is Gersten-Haber brackets? What are Gersten-Haber brackets? So first, Horseshoe differential is a differential in Horseshoe cochain complex. So let me introduce this. For any algebra, associative algebra, A, we define its Horseshoe complex. Probably better write CH, not HH, because HH is reserved for cohomology. Horseshoe complex of A as the direct sum of the following spaces. We take polylinear maps from tensor products of the algebra A with itself n times, and the sum is over n, for n from 0 to infinity, into itself. And a differential delta then is a map from home from A n into n to home from A n plus 1 into n into A, given by the following explicit formula: delta phi applied to n plus 1 elements, say A0 through AN, is equal to, first you take A0 out of this parenthesis and put it in front of everything, and then you can multiply it. But what remains? Then you subtract phi of A0, A1, and all what remains. And then you repeat it like this, alternating the signs at every step, until eventually you end up with -1 to the power, I think it's to the power n, sorry, it's rather n plus 1 phi of A1, sorry, A0 through through an minus 1 times an. So this is called the Horseshoe Differential, and these exercises to prove that delta square is equal to 0. So Horseshoe cohomology of A is just the cohomology of this complex with respect to this differential. The problem is that if you take A large enough, say A is algebra of functions, smooth functions of some manifold, then the space of all polylinear maps from A to itself is again totally wild. In order to somehow moderate it, to tame this complex, people restrict their attention to some subcomplex which lies inside this space. And this is called, I think they call differential cochains. So a cochain phi is said to be inside this subcomplex is phi of f0 fn minus 1 is given by the expression which we already mentioned, which we already met. It should be given by the sum of a multi-indices. We begin with phi I1 in minus 1 of p, and then we take d I1 of f1 and until we come with d in minus 1 of fn minus 1. Again, this expression depends on choice of local coordinates, but when you change local coordinates, you obtain an expression of the same sort. So the class of expressions is well defined. Moreover, one can independently characterize these maps, this class of maps, in totally in what they call internal way. That is the way which doesn't rely on local expressions. I'm not going again to speak about this, but well, roughly speaking, a map is a different. You have just one map, say map of which depends on just one function f, and it is differential operator. If for every point P in manifold such that there exists an open neighborhood of this map, sorry, of this point P, such that f is identically 0 at this neighborhood, then phi of f will be equal to 0 at P. So this is more or less how they describe this differential or local cochains on smooth manifolds, smooth compact manifold. There are lots of analytic constructions that is hidden here under the carpet. I'm not going to talk about this. But for our purposes, it's enough to see that when you take a polydifferential operator of this sort, so let phi be a polydifferential operator, then delta of phi, will be again a polar differential operator of a bit higher degree. I mean, degree in the terms of number of arguments it has. This is clear from the fact that when you take partial derivation of a product of two functions, and it is expressible as a combination of partial derivations of each function. So if you apply this observation, then you will see immediately that delta preserves this subspace of operations, and what you obtain is usually called the the space, sorry, the Horseshoe differentiable Horseshoe complex of the manifold. It is not very surprising that when you restrict the class of cochains in Horseshoe complex, you obtain some tools which you can use to compute the cohomology. So if you just are asked to compute the Horseshoe cohomology of the algebra of smooth functions on a manifold, and you're probably at a loss. There's no way you can do this unless your manifold is something absolutely trivial, like a point. You should either restrict your manifold to algebraic manifolds, algebraic varieties, and then you can restrict your functions to algebraic functions, and you have some chance to compute this cohomology. Or you should restrict your attention to just differentiable subcomplex of your manifold. In this case, you can, for instance, compute the cohomology using some kind of spectral sequence associated with the filtration by degrees of differential operators. But well, in any case, you can make this computation, and this computation has been done like 40 years ago, and the result is known. Theorem. This theorem is usually goes under the name of Horseshoe-Rosenberg theorem. Although Horseshoe-Rosenberg never proved this theorem. It has actually been proved by 3 people. Let me recall. Lecomte, Gut, and De Wilde, I think. So Horseshoe-Rosenberg worked with algebras of functions on varieties, on algebraic manifolds and varieties. However, they obtained pretty much the same result. So after this, and they did it like 50 or 60 years ago, and after that, this theorem bears their name, even though this result concerning the smooth manifolds and differentiable complex was obtained like 20 years after that, and by totally different people. So the result is as follows. Consider the map. Okay, I think I can use red ink here. Consider the map. From polyvector fields of M into a Horseshoe complex of C infinity of M, given by the following formula, that's coordinated by chi of, how did we denote polyvector field? Do you know? Do you remember? I probably better use some capital Latin letter. Applied to f0 through fn minus 1. Of course, we assume that p is in the sections of n vector fields. So it should be equal to the skew symmetrization probably better to reorder, but re-enumerate this from 1 to n. It's easier. Minus 1. I think there's no need even sorry, I think I'm just overthinking here. There is no need to go like so far. It is much simpler. We just take chi. Sorry, so just take p. It is polyvector field, and as polyvector field, it can be applied to a series, to the sequence of covectors. So covectors are just df1, dfn. Maybe there is 1 over n factorial. I'm not sure about this, but so this is
Gosha, look at the questions in chat.
Oh, sorry. Yeah, definitely, it is definitely graded, of course. You see, it sends n-dimensional it sets polyvector fields of degree n to cochains of degree n. So let me put it like this. I put point here, dot denotes the grading, and dot here. It will also denote the grading. So chi will preserve the grading. So this is more or less this formula. I'm not sure about this factor here in front of everything, but I think it will not spoil much thing if we introduce. The worst thing which can happen is that we have to keep trace of these terms in future, but that's not a problem. Okay, let's go on. So consider the map. Then this map induces an isomorphism of Horseshoe cohomology, differentiable Horseshoe cohomology, of course, of C infinity of M with the space of polyvector fields. This observation, this theorem is actually not very well. On one hand, it is more or less natural. It is something we can expect. It is easy to show, in fact. That delta of chi of p is equal to 0 for all p. It's easy to see. What is not easy to see is that actually the image of this map, which is usually called Hochschild-Rosenberg map, spans the whole cohomology. That's not something you can see easily. For this end, you really need some work, to do some work. But that's not the most interesting thing about this theorem. Let me go back in time a little bit, just a few minutes in time, and I spoke about.
Excuse me. Is there a ring structure on Hochschild?
That's precisely what I was going to talk about. Yeah. There is more than ring structure, actually. Yeah. Okay. Let us see. So there are two structures. So since we mentioned this, I think it's necessary to speak about ring structure as well. So first, ring structure. The wedge product on polyvector fields is something which is very naturally induced from just from the wedge product of I don't know, of exterior powers of some vector space. If you have lambda q of Tm, and you have lambda p of Tm, and of course you can define the wedge product with values in lambda p plus q of Tm. So of course now that we have the same wedge product on polyvector fields. Right? No problem. On the other hand, we have a kind of analogous product on the level of differentiable Hochschild cochains on CH diff of C infinity of M. Actually, it's not even necessary to restrict our attention to differentiable cochains, but let us do this just for the sake of simplicity. What shall we do? Suppose you have a cochain phi in CHP. Let me erase this. But no need to stick to this. And cochain psi in CHQ. How do you define phi cup psi? Well, you just take advantage of the algebraic structure on the functions. What you do, just take f1 through fp through fp plus 1 fp plus q, and tell that phi is applied to the first p functions, and psi is applied to the remaining q functions. Right? And then you can check that this map is actually well-defined, induces a well-defined map on cohomology. Which is usually denoted by the same symbol cup. Then the result, which can be obtained by some really combinatorical work. You need to work combinatorically to prove this. It is that upon the Hochschild constant Rosenberg map intertwines the cup product on cohomology with the wedge product in the polyvector fields. This is not easy, actually. It's not an easy exercise. You need to construct a certain cochain homotopy to show that this is the case. This was done by, I think it's been done by Gerstenhaber in the beginning of 1960s. And yeah, this is not something, something you obtain, something that lies on the surface. You need to work really hard to obtain, to check all the signs and to get everything, get all the cancellations on the nose. I don't know if there is a way to circumvent this detailed work. I don't know, with this subtle work. Okay, let's go on, but that's not all, because this structure, of course, is very precious and very important, but there is one more structure which has been discovered by Gerstenhaber himself, and which is even more important. to see the structure, at least to guess that this structure should exist, you need to remember that the space of polyvector fields is endowed not only with wedge product, but also with Schouten bracket. I explained you how to define this Schouten bracket, so I'm not going to repeat this. So the question, natural question which you can ask is whether there exists bracket on, well, at least on Hochschild cohomology of C infinity of M, and better still, and better yet, on the Hochschild complex of the same algebra, such that the Hochschild-Koston-Rosenberg map intertwines these two structures, at least on the level of cohomology. And it turns out that the answer is positive. And here is how this is done. And I'm really surprised that Gersten Haber was able to see this by bare hands, because he worked in 1960s without any access to computer algebra. So he did this by bare hands. So you begin with the following construction. Suppose you have two cochains. Again, phi, let it be p cochain, and psi, a q cochain. Again, there is no need to restrict your attention to differentiable cochains, because the same works perfectly well with arbitrary algebra, not just with differentiable algebra. Then you can obtain a map, a cochain, which is usually denoted by phi circle sub I psi, which will be a somewhat strange, not p plus q, but p plus q minus 1 cochain. And it is given by the following trick. You take phi, you take functions f1, fi minus 1. So you apply f phi to these functions. Then instead of the next function of the function fi, you insert the value of psi applied to fi plus 1, fi through fi plus q minus 1. But then you top it with remaining elements. So you still need, so you have I elements, you need still p minus I elements. So you begin with I plus q, and you end up with f p plus q minus 1. So this is the value of phi, comma, circle sub I of psi applied to f1 through f p plus q minus 1. And this is a very strange construction in fact, because it is neither symmetric nor skew symmetric. It does not, well, cooperate very well with differential, with Hochschild differential. It does not work very well when you try to insert it into the bracket, into the sorry, not in the bracket. You insert it into the cup product. It's just some very strange map. Horseshoe does further, he says, well, all positions I from 1 through P inside phi are equal. Moreover, we can exchange the roles played by phi and psi. And then we just take the alternative sum of phi sub I psi sum over I from 1 to P with some signs. I'm not going to speak about the signs because they're a bit tricky. Not very tricky, but well, I don't remember them at the moment. I can find this pretty quickly, but not right now. And subtract similar sum with the rows of phi and psi exchanged. So here we take the summation over j from 1 to q, and the sign is again -1 to the power, say, eta, to distinguish it from this sign. And what we obtain will be a bracket. Well, he will denote it by bracket. And this bracket has almost no properties, no good properties, except for one. There is only one evident good property of this bracket. It is that this bracket is skew-symmetric. Graded skew-symmetric. Graded.
Look into the questions of chat.
Sorry. What is the question? Well, yes and no. This is not A infinity, in effect. This is some, if you want to go into A infinity, you need to insert it further and further inside. It is close to infinity. Yeah, it is something which can be used later to obtain Tamarkin's proof of Conceived Formality theorem. This is what they call B infinity. It can be extended to B infinity, but A infinity is slightly different. Yeah, it is. You have a right. You have a correct intuition, Jiran, but this is not quite it. The intuition is correct, but details. There are some details need to be well taken care of. Okay. Okay, so this is graded skew-symmetric. Graded skew-symmetricity comes very naturally from this minus sign, which is again, well, I just use minus, but in fact it should be minus 1 to the sum to some degree. So this minus sign actually ensures this graded skew-symmetricity without no problem. But what is really surprising, it is that this map verifies graded Jacobi identity on the nose. So you don't need to pass to cohomology to obtain graded Jacobi identity here. It comes on the nose from just combinatoric considerations. Moreover, the operator delta can be now expressed in terms of this new operation, which is called Gerstenhaber bracket, by the way. This delta is just a commutator of the map M with delta of phi. It's just a Gerstenhaber bracket of M and phi, where M is the map which sends pairs of elements in A to their products. So, and which is even more surprising, it is that, well, now it is evident that delta actually verifies Leibniz rule with respect to this Gerstenhaber bracket. So there's no surprise that you can actually induce a bracket on the cohomology. And the theorem, the Horseshoe-Rosenberg theorem, can be extended to the following result. The map chi HKR induces isomorphism of creative Poisson algebras. That is to say, it intertwines Gerstenhaber, the Schouten bracket on cohomology. I think it's better to say P and Q, right? With the Gerstenhaber bracket of their images. But this identity holds only in cohomology. Only in cohomology. It doesn't hold when you just apply it to the cochains. You don't have this. So let us go on. And it is, I think it is eventually the time to look attentively at the equation I wrote. You see, this equation here, on the left, we definitely have Horseshoe co-differential, Horseshoe differential of cochains. And on the right, well, if not for the signs, which definitely should be taken care of, we have the bracket of the map given by a Poisson bracket with itself. If you go on a bit further, you see that at the nth degree, your associativity condition has the form delta Bn plus 1 is equal to the sum, to 1/2 of the sum of over P plus Q equal to N plus 1, right? I think it is now, not N plus 1, just N. P plus Q equal to N plus 1, BP, BQ. If we put B1 equal to just the bracket. Now, one can write down this expression in a shorthand notation. Put B, the formal sum, to be the formal sum h to the power k, bk. And this expression is equivalent to the equation delta B minus 1/2. Well, probably minus or plus again. I'm not sure about the sign. Maybe minus should be here and it should be plus. This looks more canonical to me. B and B is equal to 0. Now this equation is the equation that has the Maurer-Cartan form. If you remember what is Maurer, if you remember what is Maurer-Cartan equation, then you will recognize it immediately. If you don't, then you can look at this equation as equation of zero curvature. It is kind of zero curvature condition which is ubiquitous in modern mathematics. One can say that it appears in all, well, in different guises. It appears in all known mathematics, more or less, except for probably, I don't know, functional analysis. I don't think they have it there. But in algebra, in integrable systems, in geometry, in topology, everywhere it has its visitations. So now the question of finding the deformation quantization. Is equivalent to finding B in this Horseshoe differentiable Horseshoe cochain complex of degree 2 of C infinity of M with endowed with this formal power series, formal variable H. So we need to take the formal, so we can construct formal power series with the formal variable H bar and with coefficients in Horseshoe differentiable complex, such that B verifies the Maurer-Cartan equation. Now, Concevic theorem is gives you a method for doing so. I don't think I have time to speak about this theorem now because we're already running out of time. And after all, this is just the first lecture. So I'll just briefly speak what we're going to do further. So the first thing to do is to describe the set of solutions of Maurer-Cartan equations in HCH diff of C infinity of M in terms of the set of solutions of the same equation in polyvector fields and certain map between them from the polyvector fields to CH diff of C infinity of M. This map should extend the Hochschild-Kosten-Rosenberg map. So I write it in the form of Hochschild-Kosten-Rosenberg map plus something. The existence of this something of these correction terms in this so which makes this map useful for us, which actually proves that the set of solutions on the left and on the right actually coincide up to equivalence. The existence of this something, of these correction terms, is the subject of Concevic formality theorem. So next time I'm going to begin with this moment, and then I explain what kind of correction terms we're looking for. And if I have time, I'll start explaining how Concevic constructs these correction terms. because you see, first you need to reinterpret this map in certain algebraic terms and reformulate the theorem in a certain way, which will make its proof easier. Then we can give the explicit construction for these correction terms due to Kontsevich, so that in the end, we shall just apply this universal map, which usually denoted by U, to bivector pi, and it will give us automatically the element B. So pi verifies, so I conclude with the observation that pi actually verifies a sort of Maurer-Cartan equation, because this equation, pi commuting with pi, is nothing more, no less than Maurer-Cartan equation. If you remember that polyvector fields are mapped to closed cochains on the right by Hochschild-Klosner-Rosenberg map. So the differential on the left is just zero, it's just trivial. Maurer-Cartan equation is delta plus something is equal to zero, plus this quadratic term is equal to zero. Now delta is equal to zero itself, and we are left with just quadratic term. And this is just Maurer-Cartan equation. So if we eventually can construct these correction terms and this map U, which is called Kontsevich map, Kontsevich formality map, or Kontsevich formality morphism, then we can just apply this formality morphism to pi, and we will automatically get a solution to the Maurer-Cartan equation that we seek. And that's the end of the story, more or less, for us. Okay, I think I'll stop here now. And next time we'll continue from this place. And I think next time it will be, well, not online, but offline. I hope so. Okay. Are there any questions?
Thank you, Gosha.
Oh, I think that the audience is totally lost.
No, you see, there were several questions in chat and by voice.
Excuse me, as I understand, the significance of Kontsevich work is may I ask in Russian?
Yeah, definitely.
Что оно позволяет нам, в общем, упростить это вот уравнение на π и его решить. Вот это вот.
Нет, значит, давайте еще раз я скажу, по-русски лучше звучит. Смотрите, нам нужно по π построить...
Или просто вывести, что вот это вот это тождество на π.
Нам нужно по π построить b. Так? Π у нас есть. И π удовлетворяет уравнению Мауrer-Картана в поливекторных полях. Правильно? Это вот, если мы нулевой дифференциал введем в поливекторных полях, а он там, очевидно, есть, раз Hochschild-Klosner-Rosenberg отображает все поливекторные поля в замкнутые коцепи Хоушильда, значит, естественно, ввести в поливекторных полях нулевой дифференциал. Вот. Итак, там π удовлетворяет Мауrer-Картану, и оказывается, что существует отображение, вот, которое Kontsevich строит, которое по любому решению Мауrer-Картана в поливекторных полях строит решение Мауrer-Картана в полидифференциальных операторах. Вот в этих самых хоушильдовых дифференцируемых кодцепях они называются еще полидифференциальными операторами. So, yeah, just one piece of notation. The space of Hochschild differentiable cochains is often referred to as polydifferential operators. And they denoted by D poly. It is a shortcut notation for the same thing. Понятно? Kontsevich таким образом не просто упростил, он на самом деле решил задачу, потому что он эту конструкцию универсальную построил. Заметим, кстати, что отображение U, оно не единственное. Концевич предложил некоторое конкретное отображение, но есть существуют другие. И описание того, какие еще существуют, и какие свойства у них, и как они между собой там какие-нибудь эквивалентность имеют, это непростая задача, до сих пор открытая. Понимаете, там очень много вопросов возникает.
Так, а задача была, это вот то, что было в самом начале, построить
Просто
эту...
построить ассоциативное умножение.
Ага. Угу.
И эта задача, она решалась долго, упорно. Сначала ее решали для симплектических многообразий. Сначала ее решали, потом ее решили, значит, причем их решили двумя способами. Сначала это был какой-то такой ужасно занудный, индуктивный способ построения каждого нового слагаемого B1, B2 и так далее, там, до бесконечности. На каждом шаге доказывая, что такое решение существует по каким-то довольно занудным гомологическим признакам, причинам. Ну и в конце получался ряд, о котором очень мало чего можно сказать, кроме того, что он существует. Потом пришел Федосов, вот это было в прошлом семестре, и он предложил некоторую универсальную геометрическую конструкцию, довольно красивую, которая позволяет этот ряд строить геометрически, но тоже только для симплектического многообразия. Для общего пуассонного многообразия вопрос оставался открытым, потому что структура Пуассона, она может не просто иметь не полный ранг, не просто не иметь не максимальный ранг, да, пуассонова структура, в отличие от симплектической, но она может иметь разный ранг в разных точках. И поэтому все известные конструкции, которые были, они не срабатывали. И тогда Концевич предложил такой абстрактно-гомологический метод, когда просто вот добавляется к отображению Хоchschild-Розенберга некоторые загадочные дополнительные слагаемые, и в результате по решению уравнения Маура-Картана слева строится решение Маура-Картана справа. И все. Ну, как сказать, это легко сказать, трудно сделать. Просто повторяю, я видел статьи в начале, там, не знаю, там, в середине 2000-х, в начале 2010-х, которые там порядка под сотню страниц, люди просто вычисляли третье, там, какое четвертое слагаемое в ряде Концевича. Там какие-то страшные интегралы возникали. Я видел работы, в которых люди доказывали, что можно выбрать отображение U таким образом, что все коэффициенты в нем будут, например, рациональные. То есть там очень много свободы в выборе этого U. Конструкция Концевича дает только одно из многочисленных возможных отображений U. Вот.
Сейчас, я правильно понял, что это пока какие-то такие формальные вещи, там вот есть какие-то вот один комплекс, там другой комплекс, между ними какие-то отображения, а вот есть что-нибудь, что вот, вот с помощью всей вот этой машинерии решается как бы из другой науки? Не знаю, там какого-нибудь многообразия, там, не знаю, посчитали там по гомологии, ну что-то такое, чтобы...
Очень хороший вопрос. Такого рода приложения народ ищет активно. Я не знаю, честно говоря. Есть задачи, которые мы в прошлом году немножко обсуждали, но почти не успели. Значит, есть такой частный случай этой задачи, даже выясним пока про Концевича на секунду. Вернемся опять к Федосову. Если, скажем, M у вас комплексное многообразие, тогда вы можете построить звездочку умножения таким образом, чтобы комплексно-аналитические функции при перемножении оставались комплексно-аналитическими. То есть комплексное многообразие и на нем комплексно-аналитическая пуассонова структура. И можно доказать, что всегда существует умножение такое, что фи звездочка G, пси комплексно-аналитическое для любых комплексно-аналитических фи и пси. Так. Вот этих умножений, оно не единственное. Оно классифицируется с помощью некоторых классов. Давайте я сейчас не буду подробности упоминать. в обыкновенных там бернаутских когомологиях, давайте будем считать, что у нас все, скажем, Келлерово, тогда они будут в 1,1, если правильно помню, когомологиях. Не уверен в этом, но кажется так. 1,1. По-моему, 1,1. Вот. Это так называемые классы или отображения, если хотите. Классы давайте напишем в кавычках, потому что там не совсем классы когомологий. Скорее отображения из одних когомологий в другие. Неста Цыгана. Значит, я не знаю, на мой взгляд, эти классы должны быть инвариантами данной комплексно-аналитической структуры. Комплексно-аналитической Пуассоновой структуры. Симплектической.
То есть, если поменять структуру, то они не поменяются.
Меняют. Ну, то есть, если менять ее аналитически, если менять ее эквивалентную, там, в некотором смысле. Вот. Но эти классы люди не умеют вычислять толком. В этом проблема. Если бы вы, скажем, смогли их вычислить и доказать, тогда можно было попробовать там различать разные комплексно-аналитические структуры, симплектические и пуассоновые. Что происходит с комплексно-аналитическими пуассоновыми структурами, а не просто симплектическими? Существуют и на такие же классы? Я даже не знаю, если честно. То есть я не знаю, вы хотите к чему-то конкретному применить или просто посмотреть, как это связано с другими науками? Вот это связано, например, с наукой, повторяю, комплексной геометрии.
Нет, я просто так спросил, что оно находит куда-то там в реальную жизнь, так сказать.
Ну, вся жизнь реальная, я бы сказал. Просто некоторые реальности нашей жизни нам нравятся, некоторые нет. Поэтому всегда нужно уточнять,
Ну,
что...
я понял, но вот то, что я увидел, мне понравилось. Вот, да, я удовлетворен.
Нет, там много всего таких вопросов. Например, там совершенно непонятно, при каких условиях коммутирующие, скажем, у вас есть в M с этой самой Пуассоновой структурой, есть набор коммутирующих функций. Так что коммутируют они между собой, извините, по Пуассону. Вопрос состоит в том, можно ли их поднять до таких же элементов в алгебре со звездочкой умножения. Как это сказать, я даже не помню. Можно ли найти теперь f большое 1 и так далее, f большое n, такое, чтобы они коммутировали между собой? Это связано с так называемыми квантовыми интегрируемыми системами. Даже в самом простом случае, когда у вас то, что стоит справа, это хоженая, перехоженная универсальная обертывающая алгебра, а слева у вас какой-нибудь стандартный набор коммутирующих элементов, не центральных, но хороших каких-нибудь казимиров, не казимиров, хороших каких-нибудь там интегрируемых систем на алгебре Ли. Построить справа такие интегрируемую систему квантовую, ну, это не очень понятно как. Даже для очень известных систем это иногда непонятно. Вот. Ну,
спасибо. Так, у меня, наверное, есть еще один вопрос. Здесь просто в среду проходит еще один курс независимый. Он называется что-то типа «Теория деформации и кашулева двойственность». И там определили деформацию так. Это как такой категорном языке, что это просто вот как бы pullback, это такой коммутативный квадрат. Там с какими-то, может быть, ограничениями на...
Кто это рассказывает, мне просто интересно.
Гриша Папаянов, по-моему, так. Вот.
Ну, так, на абстрактном языке это можно очень много куда завести, я могу сказать. Я сейчас не хочу, ну, то есть, как сказать, я не хочу в это лезть. Я подозреваю, что это, конечно, одно и то же. Просто сам я такой категорный абстрактный язык, не то чтобы не люблю, но иногда мне кажется он избыточным. Я думаю, что если бы я взглянул на ту конструкцию, которая там, это определение, я, может, что-нибудь такое сказал бы сейчас, но сам сейчас сходу такого рода определения не вспомню. Если вы дадите какую-нибудь ссылку на какую-нибудь работу, на которую Гриша ссылается, вот. Проблема еще, что именно Гриша собирается деформировать?
Так, ну, судя по первой лекции, сейчас, он собирается рассказывать что-то про ДЖ алгебры Ли, в общем, дифференциально градуированную алгебру.
Тогда это будет очень похоже на то, что я буду рассказывать. Только я это буду очень бегло рассказывать. И вряд ли я буду рассказывать в таком абстрактном языке, как Гриша. Я предпочитаю всегда более конкретные. ДЖ алгебры Ли, конечно, тут совершенно при чем. Больше того, они у нас возникли уже. Если вы заметили.
Ну да, я заметил. Ну, это вот градуированная вот, скобка.
Да.
Ага.
Повутано, что скобка Герштенхабера с дифференциалом Хохшильда – это примеры дифференциально градуированных алгебр Ли.
Ну, я понял, я просто сейчас смотрю на программу, здесь действительно вот очень много, ну, тут уравнение Морера-Картана пишется, вот деформации декоммутативных алгебр, гомологии Хохшильда, ну, наверное, да, он действительно пересекается.
Думаю, это очень сильное пересечение, но тут разница в том, что, во-первых, у нас это, скорее всего, семинар, и мы пытаемся концентрироваться на том, чтобы еще выступали разные люди. Вот. И поэтому я, например, не буду рассказывать это весь семестр. У меня нет такого плана. Я хочу очень бегло рассказать это, ну, может быть, до середины марта, самое позднее. Я вряд ли буду рассказывать подробности про операды, про кашулевские, там, кашулевы двойственные операды и так далее. Это тоже способ доказывать теорему Концевича, но я точно, вряд ли я до него дойду. Хотя, если захотите, можно будет вас, как нашего агента Гриша Папаянова, использовать, чтобы вы потом рассказали об этом в качестве доклада.
Ну, если у меня получится там что-нибудь выучить, то хорошо, да.
Если не получится, тогда мы вам поможем, не переживайте.
Здорово.
Да, нет, тут действительно правильная мысль в том, что все-таки у нас не спецкурс здесь, а именно семинар такой рабочий. То есть он в первую очередь предназначен для изложения разных новых результатов именно студентов и аспирантов. Вот. А задачки какие-то вот мы ставим иногда, какие-то доклады такие краткие, обзорные делаем, но у нас тут нет цели прям что-то выучить или прям рассказать.
Ну, тут вот в качестве рекламы была работа Концевича, у Папаянова была, если я не ошибаюсь, такая теорема, которую, он сказал, доказали вот совсем недавно. Это что если универсальные обертывающие изоморфны как ассоциативные алгебры, то алгебры Ли у них тоже изоморфны.
Хорошо, интересно. Я не слышал об этом. А кто доказал? Ссылку вы не можете кинуть? Мне тоже интересно.
Ой, сейчас, прям сейчас не могу. Ну, кто-то русский и кто-то еще. В общем, я так не помню. Ну, может быть, чуть попозже я пришлю.
Много похожих утверждений, но вот конкретно этого я не слышал.
Он сказал, что это недавно совсем произошло.
Ну, совсем недавно, это значит до 10 лет назад, я понимаю. Если я понимаю, что это совсем недавно. Но похоже, повторяю, похожее утверждение я видал, но совсем такого не видел. И это может быть совершенно даже нетривиально, я согласен с вами. Мне было бы интересно посмотреть. Давайте вот что. Давайте тогда мы будем держать, что называется, руку на пульсе. Тут еще повторяю, та тема, которую я сегодня рассказал, это только, так сказать, одна из 3 тем, которые мы пытаемся как бы научить взаимодействовать. В природе не существует почти не пересекающихся популяциях, а мы хотим, чтобы они немножечко пересекались. Поэтому я прошу, значит, поэтому тоже это разница между нами и курсом, который вы упоминали. Поэтому я до середины марта рассказываю буду, а дальше я хотел бы, чтобы кто-то другой вместо меня на чуть-чуть другую тему. Ладно, извините, мне тут звонит мама, я поэтому, наверное, все-таки сам отключусь. Ладно?
Да, хорошо. До свидания.
Ну, я думаю, да, сегодня можно закончить. Мгм.
Всё, большое спасибо.
До свидания.
До свидания.
До свидания.